Welcome back for part two of classification and regression trees cart. So we left off creating this decision tree and we were able to interpret the decision tree. Now let's find some more interesting information that we can extract out of the decision tree. So decision trees, fair warning, is not the best I have found in my personal experience, so I am expressing a personal opinion, are not the best. Classification and regression tree is not the best algorithm for making predictions. However, it is excellent in visualizing your data and seeing what variables are important, what makes sense. So let me just run this again. Okay, so we have a better graph, how it looks a little smaller. Okay, one of the things that we can extract is, again, the decision tree is stored right over here in this object called CT1, okay, which is classification tree 1. I can extract the variable importance by doing this, CT1 $variable.importance. If we go over here and open this up, we can see that it's a list of things. A list of things is like a box full of stuff. And within the stuff, we find something, many things, but there is something called the variable importance. So let's see if we, here it is, variable.importance, okay? And it has some stuff here. Well, let's take a look at what this thing actually is. So let me just close this up because this is, I get it, it's confusing. But just to show you, I can run just this little portion, okay? And I get this. But I like seeing things in a data frame, so I'm just gonna run this output. I'm gonna make it a data frame, and then I'm gonna store it into this new table called variable importance. So let me just run this, and I can take a look at variable importance. And as you see, it says, it gives these scores, okay? And it's nice that it gave it to us in descending order. And it says, well, what's the most important variable? Rating. Then the next important variable is age. Then occupation, which quite frankly, from the logistic regression model, I don't believe too much. But, you know, we're dealing with the training data set, which is 406 observations, and, you know, things can be a little clunky. But by far, rating is the most important variable. And we can confirm this, and usually this works out pretty well, where the variable importance says rating is the most important variable. Well, your first split is usually, if not always, on your most important variable. Then your next split is on your second most important variable. But as you see, your next split is not your third most important variable, it's years married, which is your fourth. And your fourth split is on occupation, which is your third most important variable. I believe more years married being important, and if you recall the logistic regression, age, I believe, did not play a factor in predicting very well. So, but you know, different algorithms have different methods to predict, and that's why we try different things. Okay, so now I can see which are my most important variables. Who cares? Well, if you were to know just one thing about someone, you can only know one thing about someone, and you want to be able to predict as accurately as possible whether they're a cheater, the one thing you'd want to know is how they rate their marriage. Okay. We've covered variable importance. Now let's look at another statistic, another little point of data here called the CP table, okay? This is talking about splits, okay? So, we're talking about how far down the tree is going to go. And at times, you're going to want to prune this tree, meaning if you get a tree which seems to be just way too big, and what I mean by way too big is that your terminal nodes, as you see, I have 85%, 2% of the data, 3% of the data, 2% of the data, 7% of the data. Sometimes you don't even, 2% of the data in a data set that has 10,000 observations, well, Well, there's 200 people here. But 2% of the data here, 2% of 400 is about 8 to 9 people. Well, do I really want to make a decision, a rule, based on what 9 people did? Probably not. So I want my tree smaller, and well, what I really want is for these terminal nodes to have a bigger proportion of the data, not 2, 3, and 2%. Okay? So I'm going to prune that tree. These numbers over here are going to prove valuable to be able to use this CP equals something. So here I have 0.01. Let's see if this works. Sometimes it's a little tricky. So I'm going to induce a number greater than 0.01, which is 0.015. Okay, let's take a look at our tree. And it created the same tree. Well, how about if we use a number greater than 0.33, such as 0.034? Run this. Not good. Just gives us that. Well, how about if we do something in the middle? 0.02. There we go. Still not good. Nope, not doing it. So unfortunately for us, if we try to prune this tree, because on this over here, I'm sorry, these statistics, because we only have 2 lines, it's either just this or everything else. So what you're going to want to do, okay, if we re-scramble the data, okay, meaning that I redo all of this, get another set of random numbers to get another random split on the data. As you see, before we had 406, now we have 421. We create another tree. As you see, the tree looks now different. Every time you select a different random set of numbers, it'll be different. And the variable importance could also change. But this is the most important part. Now we've got 3 levels, okay? So 0.023, okay? In your homework data, you won't be having this issue because there's a lot of data. So I'm going to set my CP to something bigger than this, but smaller than this. So I'm going to do 0.024, and you're going to see how the tree prunes. Oh, sorry. Two, 4. Run this. Now look at the tree. It pruned up. I have 2% of the data, 4% of the data, 8% of the data. Before, what we had was 84,222,428. Well, not that it improved too much, but with bigger data sets, it'll work better. Now, let's go over here to let's create, using the validation data set. Moving on, we are going to create a new variable called predicted cheater, cheater predicted. Basically using our second model, okay, the one that's pruned, okay, and our validation data set. Okay, let's run this. Let's take a look at that validation data set. So we have our variable cheater and we have predicted cheater. As you see, it has 1s or 0s. If we would have created a regression tree, it would have given us a number between 0 and 1. This is now solving what logistic regression stops short of, is saying what's our cutoff. This is giving us a acute prediction, whether it's cheater or not. Then I'm going to move over here just to see, you can see that the predicted cheater is a factor with 2 levels. And last but not least, let's create our confusion matrix, okay? So this is where we're going to create our confusion matrix, okay, where we're going to see, we are going to see how well this model is working. And by that, again, here we have our proportion of row, proportion of column, proportion of table. So here we have cheaters and non-cheaters, predicted non-cheaters, predicted cheaters. So out of this row, which is cheaters, 75% are cheaters, we were able to classify correctly the non-cheaters, 95.6% of them. We misclassified 6, which is 4.4% of them. Out of the cheaters, again, this is the actual cheaters, we have 44 actual cheaters. We missed, again, we predicted that they're not cheaters. We missed 84% of them. We classified correctly 15.9% of the cheaters. If we want to see what the overall error in classification is, again, these proportions are table totals, okay? So this is a person that is not a cheater, that we classify them as a cheater, 3.3%. In 20% of the data that were cheaters, we misclassified them, okay? So basically 23.9% of the data we made mistakes on, okay? But we were able to capture 7 cheaters. Whether you believe this is a good model or not is up to you and what your business, what is the cost of making this error? What is the cost of making this error? And that's it for classification and regression trees.